Welcome. I'm going to start a new chapter, that is solid state. So we know that states of matter are three types. One is solid state, another one is liquid state, another one is gaseous state. So from these three, how can you distinguish that this is solid state and this is liquid state and this is gaseous state? For that, we have mainly two properties. From that we can distinguish that this is solid state, this is liquid state, and this is gaseous state. The two properties are one property is on the basis of intermolecular force of attractions. Intermolecular force of attractions. On this basis, what we say that solid state has highest intermolecular force of attractions. Solid state. Then we have that liquid state. Then we have the gaseous state. And next, on the basis of thermal energy. On the basis of thermal energy, and according to this thermal energy, what we see that first we have gaseous states, and we have then liquid state, then we have that solid state. So from here we see that if it is a liquid state, so if it is a gaseous state, then what the conditions will be there? That should be that highest thermal energy, that's the intermolecular force of attractions, and the lowest thermal energy. So for solid states, what we need, that it has to be highest, that is intermolecular force of attractions, intermolecular force of attractions, and the lowest thermal energy. These are the conditions needed for a solid state. And also we know that the solid state are two types. So we get the solid state also in two types. Solid states we get, that is two types. One is crystalline solids, another is amorphous solids. So what in the crystalline solids, it has a regular shape. So I am first distinguish on the basis of shape. So on the basis of shape, what is say that it has regular shapes, it has regular shape, and it has irregular shape. It has irregular shape. Okay, on our which basis we can distinguish? That second basis we can distinguish is that on the basis of melting point. Melting point. What it has? It has sharp melting points. And for this it has a range of melting points. That is that it will melt at a let's say it may be made from 1012 let's say 1 0 10 melting points, but in this edge it is a sharp melting point, means it will melt only 1 0 1, means it will melt at a certain melting points, at this only it will melt. But in this case it may be melt 1 0 1, it may be 1 0 2, 1 0 3, up to 1 0 10. So it has this range, within this range it will melt, but for this it is a sharp, means one melting point, on that it will melt. And second way we can distinguish, that is for fusions, on heat of fusions we can distinguish what it has. It has definite heat of fusions, whereas it has infinite heat of fusions. It means that at a particular time it will be the heat of fusions will occur, but here that infinite that a particular range it will do the heat of fusions. So it has infinite heat of fusions, where it has a definite heat of fusions. And second way we can distinguish is that it has long range order, and for this it has short range order. And another, the difference between the crystalline and solid state is that it is true solid. It is true solids, but it is pseudo solids. It is pseudo solid, or we can say super solids. Okay, and what are the examples for this? So for crystalline solids we say that KNO3, that ionic solids, or it may be, we can say that for metallic solids we have that copper, and for covalent solids that silicon compounds. Okay, and for amorphous solids the examples, like you will see that rubber, this type of plastics, and this type of glass. So these are all examples of amorphous solids. Okay, so now we've seen that this is the crystalline. So solids can be two types, one is crystalline solids, another is amorphous solids. On these crystalline solids, for making the crystalline solid, what things are needed? Let's say for crystalline solids is made by one unit cells. Okay, and for unit cell is made by lattice points. It means that what we need, that first lattice point we need it, after lattice points we by lattice point we will make unit cells, and that unit cell will helps to make that this crystalline solids. Okay, so similar, like we have that cells, on that cells we will make the tissues, and from the tissues we will make that organs. So similar way we have we need first lattice points, and this lattice point will help to make unit cells, and this unit cells we will make that crystalline solids. So in this chapters of solid state we will discuss on this crystalline solids, and we will not discuss about of this amorphous solids. So we will mainly discuss about of this crystalline solids only. will not discuss about amorphous solids, okay, because it is a pseudo solid, it is not a true solids. And note that these amorphous solids can be become a crystalline solid by heating at a certain temperatures. It means that by heating amorphous can be made crystalline solids at certain temperature. So that from amorphous also we can make a crystalline solids if you heat at a certain temperature, at a particular temperature, that amorphous will convert into a crystalline solids. Okay, so now in this solid state units we will discuss on that crystal solids, crystalline solids. Okay, so we see that for making these crystal solids, what things are needed? First we need that solid state, lattice points, and using this lattice point we will make a unit cells. After that unit cell we will make that crystalline solids. Okay, so now we'll discuss that what do we mean by lattice point, and how we'll make that unit cells, and how that unit cell will helps to make a crystalline solids. So first we'll discuss about of lattice points. So what is the lattice point? It is the substituent of crystalline solids which can be any atoms, or it can be any particles. So using this we will make a which can be atoms or any particles which combines to form a unit cell. Okay, so from this lattice point we will make a unit cells. And now what is the unit cell? This is the importance. Okay, so from this lattice point we will make the unit cells. Okay, now this unit cells, this is the basic fundamental units of a crystalline solid. So first write that it is the smallest unit of the complete lattice points, complete crystalline solids. Whatever the crystalline solids, for that the smallest part is the unit cells, which repeat again and again, in all possible directions, to form the complete crystalline solids. So this unit cell is the fundamental units of a crystalline solids, or it is the smallest unit of a complete crystalline solids, which repeats again and again in all possible directions to form a complete crystalline solid. So this crystalline solid, if I search, let's say this is a crystalline, this is a unit cells, this is the unit cells, this is the unit cells, and these are that, let's say, the lattice points. So these lattice points will help combines to form a unit cells, and these unit cells, what that this is the smallest part of a complete lattice points, complete crystalline points, which repeats in all the directions to form a complete crystalline solid. Let's say this is one side, and again if I do that, this sides, these sides, and again this will go to these sides, again it will go to these sides, again this go to these sides. Okay, so in all the directions, and it may be in the above directions, that is above directions, and in the below directions. So in all the directions, this crystalline, this unit cells, this form a complete crystalline solid. This is the complete crystalline solids. So that that unit cells, this the smallest part of a complete crystalline solids, which repeats in again in all the possible directions to form a complete crystalline solids. Okay, like for making a wall, we want to make a wall, then what that we will do the bricks, and this bricks will do that, this bricks will make the wall by all are bricks, and these bricks when they combine, and they will form a complete wall. Likewise that unit cells, it will that is the smallest part, means that what I want to say, that if we have a unit cells, and all the if you make more and more unit cells, and that unit cell you combine, you join in such a way that all the directions will join one unit cell, then that will form a crystalline solids. Okay, now whenever we made a crystalline solids, so this crystalline solids, and we say that what do you mean by crystalline solids, that is a that is have a regular shapes, and how it will distinguish it as a sharp melting points, and it has a definite bit of fusions, and it is a long range order. Long range order means all this order, all in everywhere we get that same types of orders. Okay, another one points I forgot to mention here, the distinguish can be done. Another example, another way is that this is anisotropic in nature, and this is isotropic in nature. Isotropic in nature, what do you mean by anisotropic in nature? Anisotropic in nature means that its physical properties are different in all directions. Its physical properties are different. Okay, the physical properties are different in all directions, whereas isotropic means in different, it has a same physical properties in different sorry, it has the same physical properties in different directions. So same physical properties it has in all directions. That what mean that this is anisotropic nature, that is anisotropic in nature. Okay, so that's what it mean that crystalline solids. So how you make that crystalline solid, that we have seen. Now one properties of a unit cells. We will discuss the properties of a unit cells. Oh, sorry, properties of a crystalline solids. Properties of crystalline solids. What we say that let's we make any crystalline solids. So let's say this is one crystalline solids. Now you will make by making unit cell, we make this crystalline solid. Let's say this is the crystalline solids. So what the property it says, let's say this is a crystalline solids. What its property says that in this angle, at any point, let's say these points and these points and these points, so it has some interfacial angles. Interfacial angle means that adjacent face. Adjacent faces means, let's say adjacent means nearer. Okay, this is one space, this is another space. So in between this space or in between this space, what have that they have some angles. Between this adjacent face they have angles. Let's say if I have it, let's say these molecules, and now what we see that here, what we see here, if you look this is one space. Let's say this is one space and this is one space. So these are the adjacent space. In between space, whatever the angle, okay, this space and this space, in between this space, this angle is 90 degree. This and these are perpendicular, this and these are perpendicular. So what we see here, let's say this is the front space, this is the front space, and this is the above space. So this front space and above space, but the angle is 90 degree. Okay, so this space, this space, this space and this space, this space and this space, the angle is 90 degree, because this and this and these are 90 degrees. So what we say that interfacial angles, what do you mean by interfacial angles? Let us say that any two adjacent space, angle between, the angle formed by any two adjacent faces, the angles formed by any two adjacent faces, or the angle formed between any two adjacent faces, or we can say here between any two adjacent faces are interfacial angles. Interfacial angles, it means that angle between this and this angle. So these are called interfacial angles. So why I'm interested about of interfacial angles. So let's say this is above space, and let's say this is adjacent space. So in between that angle is 90 degree. So this interfacial angle, this is the adjacent space. This is one space and this one space. They are nearer. They are joined with each other with this edge, with this common edge. Okay. So these are adjacent faces. So this adjacent faces, any angle it will form, that angle is called interfacial angles. Okay. And these interfacial angles that we say that law of constancy interfacial angles. What it says that the interfacial angles let me check it. The interfacial angles for a particular crystal lattice remain constants even if size and that is size and okay, so interval remain constant no matter what is the size of the unit cells. No matter what the size of the unit cells. It means that this interfacial angles, if that is let's say 90 degree, now if you increase the unit cell, if you increase the crystalline solids, then also that interfacial angles remain constant. Okay, so that what that importance of interfacial angles, that if you change the size of a unit cells, it means size of the crystalline solids, then also that interfacial angles will not get affected, that will remain constant as it is. So that's the laws of constancy interfacial angle search. Okay, and the interfacial angle means that angle that is formed between any two adjacent faces. Now we will move to that types of unit cell. According to types of different types of unit cell, there will form different types of crystalline solids. Okay, so based on unit cells, we will get the two types. Based on unit cells, we can categorize into two types. One is primitive unit cells. Another is non-primitive unit cells. Okay, so in primitive unit cells, what things are there? So this unit cells is made by the lattice points. So in primitive unit cells, that lattice points are present only on the corners of the unit cells. Let's say if we have this is a your unit cells, so that this lattice point will present only at the corners, these corners and these corners and these corners. So primitive unit cell means that lattice points, because unit cell is made by lattice points, so that lattice points are present only at the corners. That is called the primitive unit cells. Whereas for non-primitive unit cells, lattice points are present on corners with some other some other with some particular centers. Okay, so that is present for non-primitive unit cells, that is present in the corners. With that it is present, that lattice point also present with some other centers. Okay, but for the primitive unit cells, these lattice points are present only at the corners, but here with corners, with that it presents some other centers also. Okay, that is called non-primitive unit cells. So if you have that so this primitive unit cells like simple cubic lattice, that says this. Here examples upon crystalline solids, that is primitive crystalline solids, are like this, where that lattice points are present only at the corners. Okay, whereas for this, that depends on that it is present with corners. Here for this case, with corners, the lattice point may be present at that base centers, it may be present at that edge center. So that depend on that, where that type of uh, crystalline solids we have. So for now, what we are going to say, that for primitive unit cells, that lattice points are present only at the corners, and for non-primitive unit cells with corners, some other points also lattice points are present. Okay, so we are more interested on non-primitive unit cells, non-primitive unit cells, where the lattice points are present at corners plus at some other specific centers. Okay. So this primitive unit cells, can be classified. Primitive unit cells can be classified into first is let's say this is SCC, simple cubic unit cells, and there is we have that FCC. Okay, that is face center cubic, well face center cubic, another is BCC, body center cubic lattice, another is end center cubic lattice, another is edge center cubic lattice. So first is based on unit cells. We have the primitive and non-primitives. Okay, and for primitives, what is said, based on the primitive unit cells, we have that SCC, that is simple cubic unit cells. This is simple cubic unit cells, and this is face centered cubic lattice, and this is body center cubic lattice, and this is end center cubic lattice, and this is edge center cubic lattice. Okay, just a minute. Let's see, that is sorry, for this SCC, this will comes under, that is primitive unit cells. This SCC will comes, that is only at the corners. Okay, so SCC, this will comes under primitive unit cells. So we have the here is FCC, BCC, end center and edge centers. So for this we have that these four types, that is FCC, BCC, end center and edge centers. So FCC means, for FCC, what is there? Suppose this is the crystalline solids. So lattice are there, lattice points are there at corners, all corners. With that lattice points also present at the face center, that is face center. So this is face, this is the above face, this is below face, this is side face, this side face, and that is back space, and this is front space. Okay, so that lattice points are there with corners, plus face center. Okay, and for body centers, corners plus one body center. Let's say for this, if I make that, so so here all corners will be there with that one at the body center, that is in the middle. Okay, one will be there at the body center. Whereas for end centered, what will be there? Here also corners plus end center, means that opposite, any two opposite faces, any opposite faces at the center, one lattice point will be there. So corners, any two opposite faces, opposite face centered. Okay, so let's say if I make this, that is, so at all the corners we have that lattice points, with that any two opposite faces face centered lattice point is there. Let's say if we make here above and back, this is opposite spaces, so here is present, then also it's fine either here, or if you are not doing that, any two opposite spaces either here. Now if you are not doing here, then let's say you do here and here, means any two opposite space centered lattice points are there with corners, then that is called end centered cubic lattice. And for edge centered cubic lattice, although this is not exist, this is hypothetical lattice. Let's say here that all that ends and all that corners plus here what that there every edge centers, at the edge center lattice points are there. Okay, so here corners plus edge center. Okay, so that is called that this type of non-primitive unit cells. And that primitive unit cells only SCC is that where all where for this case lattice points are there only at the corners. Okay, this is the SCC, that is simple cubic crystals. Okay, so this is that primitive non-primitive unit cell, this is the primitive unit cells. Now what is the contributions of these lattice points? Let's say we have body centers and we have that base centered and we have that end centered and we have that edge centered. So if that lattice point, now that is the contributions of lattice points. So if it is at body center, then what is the its contributions? Let's say this is any unit cells. But contributions of lattice points for unit cells for unit cell. Okay, so let's say this one, let's say this is the unit cells for the case. Now that lattice point is present, let's say lattice point is present at the body center. It means that it's at the body that lattice point is present. On that case, what is the contribution? So that is fully in the body center, so that contribution is always 1. Contributions is 1. Okay, now if that lattice point is present at the base center, so at the base center, if it is present here, the lattice point is present at the base center, then what is the contributions of this lattice point to this unit cell? Let's say this is the unit cell, this, let's say this is the unit cells, and if that body lattice point is present at the body center, let's say this, its contributions is 1. Now if that this is the unit cells, now that lattice point is present at the base center. So let's say this is that this is the full crystallines and this is the lattice, and in this this is the unit cells. Now that that is contributions. Let's check. Okay, so now let's say this is lattice points. This is the lattice points, this is unit cells. Now that okay, so let's say let's say this is a lattice point, lattice points. Now it is present at the body center. It means that it is present at the middles. Okay, now it is present here, this one. So now if you pull this here, and if you do that all the directions, then what is contribution? So it contributions is 1. Always body center means contribution is 1. And for the face centered, what you see that if it is present at the face centered, then let's say it is present in this face. This is the face. Okay, this is the face. These are the face centered. Now if that lattice point is present at this face center, then if you do another one to here, another unit cells here, then what you see that lattice point which is present in the middle, that will be fully covered, means that is not look from outside. It means that this face center is contributions is 1 half. Contributions is half. Okay, so assume that this is a rectangular unit cells, and that lattice point is present at the face center. Then if you take the 2 unit cells, then that will be completely not look from outside, means that contributions is either that lattice point is contribution is this space and this space, only 2 space. Another unit cell will come, then that this lattice points is not contribution to this, means this is not joining, this is not mixing with this, means this is present only this. After 2 lattice points, after 2 unit cells, this lattice point is completely covered. It means that its contribution is half. Now the case is that whenever it present at the end center, I will look that, then we have that body centers, sorry, corners, and we have that end centered, end center, and there is edge center. Okay, end center is nothing concept is there, that is edge center. Okay, so now if the lattice point is present at the corners, let's say that lattice point is present at the corners of the unit cells, here that unit cell is present in this corner. Okay, now to cover these corners, I will take 1 unit cells here, again this is there, again I will take 1. Okay, so let's say this is the corners. Okay, to cover this I take 1, still it is here, then I take another one, still it is here. If I take another one, still the corner is there. So if I take another pore here, then this point will be completely covered, means that to cover the corner I need 8 unit cell, means that contribution is to the 8, means that will contribute to 1 upon 8, means that it to cover it we need 8 lattice that is unit cells, means that contribution is to 8 that is unit cells, means that is 1 upon 8. Okay, means for to cover 1 we need 8 that is unit cells. Okay, for edge center, if it is edge center, let's say this is edge center, to cover this how many I need? I want to cover this edge. Okay, so 1 I need. Okay, another if I take, then also one side it is looking. Now if I take another, then this point, this edge is completely covered. Okay, this I want to cover this one, so 1 take I, another if I take, then this is complete cover, means I need for unit set. So edge center is contribution is 1 by 4, whereas corner contribution is 1 by 8, face center that contribution is 1 upon 2. Okay, so this is the contributions of lattice point for unit cells. Okay, now we will look that contributions of this lattice points for unit cells in BCC, FCC and end-centered crystalline solids and edge-center crystalline solids. Okay, so now we have to look for the unit cell. Now we are going to look for the BC for completely crystalline solids. Okay, so for if I say that for BCC, how many that lattice point, how much contribution is due. So it is first at the corner. So for corners, that 8 are there, 8 corners, and that corner contribution is 1 upon 8. Okay, with that one body center is there, and body is contribution is 1. Okay, so total contributions of lattice point for unit cells in a crystalline solids, that will be going to be 2. Okay, so this is also written as Z. Okay, so this Z is equal to 2 for BCC, and for FCC, okay, so the Z is equal to, that is the contributions of lattice points in a crystalline solids, that is, so first is corners 8 and its contribution is 1 upon 8, and it has the face, and face, how many spaces are there? You see that in a crystalline solids, so this is let's say it's one crystalline solid, so this is cubic, let's say this is a cubic crystal, then how many edges are there? 1, 2, how many faces are there? First face, 1, 2, 3, 4, 5, 6 spaces are there. How many corners? 1, 2, 3, 4, 5, 6, 7, 8 corners. Okay, how many edges? 1, 2, 3, 4, 5, 6, 7, see, 1, 2, 3, 4, okay, 5, 6, 7, 8, okay, 9, 10, 11, 12, so 12. So first we will look that for cubic crystals, corners are 8 and face are 6 and edges are 12. Okay, so this face are 6 and contribution is what we have seen, that face, then its contribution is 1 upon 2, so this will going to be 1 and this going to be 3. So this for FCC, Z is equal to 4. Okay, for BCC, Z equal to 2, and similarly for BCC we've seen, FCC we've seen the end center and edge center. Okay, and for end center crystalline lattice, what, that is 8 corners, 8 and contribution is 1 upon 8, plus for end center, any 2 opposite faces, means that 2 faces I am taking, and for face contribution is how much? 1 upon 2. So this cancel, this cancel, so this is going to 1 plus 1, that is 2. So this Z is equal to 2. Okay, similarly for edge center and edge center crystalline lattice. Okay, this is not exist, this is hypothetical. So end center, edge center, so corners are 8 into 1 upon 8 plus, okay, edge are 12 and contributions is 1 upon 4. So this is going to becomes this is 1 and this is going to be 3, so this is again going to get the 4. Okay, so this is the how to calculate the Z value, that is the contributions of lattice point for unit cells in a crystalline solids. Okay, so now we have discussed that based on unit cells we classified that how the lattice points are present in a unit cells. So that are two types, primitives and non-primitives, and in primitive only SCC will come, and in primitive SCC, that is simple cubic unit cells, that is lattice points are present only at the corners, whereas for non-primitive unit cells, that lattice points are present with corners, they present with some specific centers also. Like if it is present at base center, then that is going to be at base center crystalline solids, and if it is present at that edge center, then we have that edge center crystalline solids, and if it is present only at the body center and with corners, then we have that body center crystalline solids. So another classifications based on unit cells, the classifications classifications of unit cells based on axial length and interfacial angles. So we have discussed about of the interfacial angles and axial length. Let's say this is any crystalline solids. Now this is that, let's say any sides, this, so these are called that axial lengths. These are called that axial length. Let's say this is A, let's say this is B, and let's say this is C. Okay, so this A, B and C are axial length, and interfacial angles are this is alpha, let's say this is beta, and let's say this is gamma. Okay, so these are the interfacial angles, that is alpha, beta, gamma are interfacial angles. So based on this, we have that different types of unit cells. So that classification will say that here I write unit cells, here I will write that axial angles, here I will write that unequal number of axial length. Okay. Number of unequal axial length. Okay, and now here I will write that interfacial angles. Okay, so what I write that based on that axial length and that interfacial angles, axial length, and this is axial length. And interfacial angles, we have the different types of unit cells. First unit cells are, let's say that is, we write here, first unit cell is cubic. Okay, so I'm writing that first which have that interfacial angle is 90 degree, that is alpha equal to beta equal to gamma is equal to 90 degree for cubic. Okay, so first I am writing that unit cells which have that alpha beta gamma equal to 90 degree, that is one is cubic, and second is we have that tetragonal. This also have that this one, you write some things and you write something, this alpha beta gamma equal to 90 degree. For tetragonal also this you write, here also we have that alpha beta gamma equal to 90 degree. But first cubic, then tetragonal, then we have that orthorhombic also. We see that alpha beta gamma is 90 degree. Okay, rhombic, that alpha beta gamma are equal, but that's not equal to 90 degree. but that orthorhombic, that is 90 degree. Okay, so we know that rectangular and square, so they have that all 90 degree, whereas for rhombus all sides and angles are equal, but that angles are not equal to 90 degree. Okay, so here we see that it's all angles and all sides are equal, but that angle is not 90 degree, so that is rhombus. But orthorhombus, that angle is 90 degree. Okay, so ortho, first cubic you will write, then tetragonal, then orthorhombus. So rhombus. Okay, so here also alpha, beta, gamma equal to 90 degree. Okay, so please order it, that should be first cubic, tetragonal, then orthorhombic. Okay, then we have that which are not equal to 90 degree, that will start. So first cubic, then tetragonal, then orthorhombic, not cubic orthorhombus, first or cubic, tetragonal, then rhombus. Then we have that which have not 90 degree angles, that we will write that first we will write monoclinic, first monoclinic, then triclinic. Okay, first monoclinic, so it is also this, and here that alpha equal to beta, but this gamma is not equal to 90 degree, and this is not alpha equal to beta, and that is not equal to gamma, and gamma is also not equal to 90 degree, that is monoclinic. Okay, and for triclinic, it has that this here for axial angles, this triclinic, monoclinic, this is based on that axial length, this is not based on that angle. Okay, here also you see that alpha equal to gamma, but that is not equal to beta, and beta is also not equal to 90 degree. Okay, so this is not equal to 90 degree, this that is, let's be a minute. Yeah, I see. So this, next, oh okay, sorry, this monoclinic, what we see that alpha equal to gamma, okay, not beta, and beta is not equal to 90 degree. Okay, also this alpha equal to gamma, but that is not equal to beta, and for triclinic, that alpha equal to gamma, so this is alpha equal to beta, alpha equal to, this is also huge. Yes, for triclinic, for axials as well as interfacial angles, all are not equal, so alpha not equal to beta, not equal to gamma. Okay, so for triclinic, okay, all are not equal, and this angle. Okay, so first we will write that cubic, tetragonal, rhombus, then we will start with monoclinic, then triclinic. Okay, next we will go for that next is hexagonals. This also you see that this alpha equal to beta, and gamma is not equal to 90 degree, and this gamma is generally this is 120 degree for hexagonal. Okay, and last we have, that is rhombohedral. Rhombohedrals. Okay, so it is uh, alpha equal to beta equal to gamma. You see that for rhombohedral all are equal, but that is not equal to 90 degree. Okay, so this is the order for crystalline solids, and how these angles will be axial length. I am written about of interfacial angles. Now this number of unequal axial lengths, this is start with 0. The first will be 0, then 1, then 2. Okay, and from here also we start with 0, this is 1, and this is 2, and this middle one is again 2. Okay, so this is the order. Now this is interfacial angles are ABC. So I will write A equal to B equal to C. I'm just writing A equal to B equal to C. This is A equal to B equal to C. This is A equal to B equal to C. This is A equal to B equal to C. This is A equal to B equal to C, and this is A equal to B equal to C. Now we will do that here 0. So do unequal from right side. Okay, so here 0, so I will not do. Here 0, 1, so from right side unequal 1. Okay, here 2 from right side 1, 2. Okay, here also 2 from right side, so this 2. Here also 2 from right side, so this is, and here 1, so 1, and this is the axial length for unit cells and interfacial angles. Okay, so this is the classification of unit cells based on the axial length and interfacial angles. Okay, so in the previous class we will discuss more. Today after this, thank you.